Don Pettit here from NASA. I'm at home due to the COVID-19 virus, working from home, still working on the lunar lander and the Gateway spacecraft. And I'm going to talk about habitability in spacecraft. Let's start off with the second most important activity that most human beings do after they get up in the morning. Get yourself a cup of coffee. We do the same thing on orbit. You float to the galley and you make a bag of coffee from the hot water dispenser and a pouch that has freeze-dried coffee. And this is an important ritual for not only human beings on the ground, but also human beings living and working in space. When you are an engineer designing a spacecraft, you need to be able to work a few pleasantries into it that are an ingrained part of our human culture. And having the ability to have a cup of coffee in the morning is part of the deal. How do we make our proper cup of coffee when we are living and working on the space station? And probably how will we do this on the Gateway Lunar Orbital Complex? And when we make the lunar landing vehicles for surface operations on the moon, how do we plan to make the coffee? Let's start off by looking what we do on the International Space Station. If a regular coffee cup won't work in an orbital environment, what can you do to transcend from drinking your coffee through a straw from a bag into something that's more fitting for a proper cup of coffee? This is a zero-gravity coffee cup. And this cup will work in a weightless environment. Here is a video of this coffee cup on orbit during STS-126. And I put some tea in it, and notice how the surface tension coupled with the wetting angle makes the tea creep up the side that has the acute angle. And there's Steve Bowen and I. We are toasting and having a proper cup of tea. So now, for the first time, we as a crew, we can have a proper toast. We can drink and share our tea and coffee in a manner commensurate with people on Earth. Here we have Earth Cup, first version of a space cup, working with a colleague of mine, Mark Weisslogel from Portland State University, along with his graduate students. We came up with a second generation design. This is 3D printed, and the shape of this cup is dictated by the mathematics of fluid physics in a weightless environment. Let's watch a short video. It's a lecture that Mark Weisslogel gave at Portland State University about the fluid physics behind the zero-gravity coffee cup.
So let's take a break now. This has really been a difficult subject. I know science is hard for everybody. Okay, and let's talk about this. Okay, so I'm going to call this the math break. And this could be really wrong to do. But I want to show you something. And I want to show it to you. I don't want to tell you it. I'm going to show you. So you're going to get it right here. It's going to take about a minute and maybe 20 seconds, maybe 10 seconds. But let me show you what is done here. This is just coffee, but this is what we do. That there is a schematic of the flow along this corner. Get ready. Okay, here's a tip. Here's a tip. Just kind of watch. Don't listen. So I'm going to speak, but it's going to be like elevator music, right? That's the flow. Here it goes. Ready? These are the Navier-Stokes equations. There's 27 terms. 3 equations. They balance momentum along this flow. Okay? It's a nonlinear equation, never been solved, ever. Here are the boundary conditions that apply to it. They're very complicated. Some of them have physical quantities that we don't even understand in terms of physics. If the flow is slender, there's predominantly one direction of flow. So this equation is small, so we can ignore it. It's small, not zero. Same is true for this equation. So primarily, the most forces must balance along the z. That's this one. If gravity is small, which it is in space, if the flow is slender, that's true. And if the flow is really slender, then inertia is completely eliminated by the fact that this is pretty much a long, slender, one-dimensional flow. If that's true, only these terms matter. This is the capillary pressure, and these are viscous terms, solved in this cross-sectional domain. If I apply the no-slip condition here, it simplifies, and if the flow is slender, I get this great simplification of a nonlinear partial differential boundary condition. It breaks down into simply the contact angle condition. If I apply those two to this equation, I can integrate this equation twice, solve for the velocity, take that velocity field in this domain, integrate it twice, get the average value. If I get the average value, I can calculate the volumetric flow balance here, which gives me this transient term for the mass conservation. If I then take this average velocity, substitute in that equation, and then recognize that this cross-sectional area can be expressed in terms of the height of the meniscus squared times this dimensionless geometric function. I can substitute that in and get this nonlinear second-order partial differential equation for the evolution of this surface along this edge in time. Got it? Okay? Okay. Okay. We're 1/3 of the way. No, two-thirds. So let's apply that to the astronaut coffee cup. Ready? Okay, if I define the amount of volume that comes out into his mouth as Q, and I identify the location of the bulk meniscus as it recedes into the cup as Z2, I identify a boundary condition here with something we call Kunkes fin theory. If I then take that equation that I just derived on the previous slide, I solve it for the free surface there, I can actually compute the drain rate into his mouth. It's a function of this thing, Z2. I apply then another boundary condition here at this boundary condition. I get a differential equation there that I can integrate and get this value for Z2, which I substitute in there, get the flow rate. Now I'm done. Okay, that's it. All of that stuff to get these things, and this is what engineers want. We want to be able to specify what the heck is going on as a function of all the junk that's in the problem. So this is the drain rate, but this is the drain rate, how much you can take in. It tells you that this cup can develop that much flow rate and put that into your mouth. It's a function of everything we care about. The surface tension, the wetting characteristics, the viscosity, the size of the container, the shape of the container, the interior corner, everything in there, even time. And we get this cool power law behavior and all this stuff. This is what you want. It's just coffee. Okay, this is the comparison. There's the data. Those are data points from drain rates, and there's the theory right there, right on top of it.
As you can see from Mark's lecture, the fluid physics behind how the zero gravity coffee cup works is straightforward, but can be rather involved. So now we can drink our coffee in a manner consistent with everybody on Earth when we are in space. But where do we get the water to make our coffee from? Here's a picture of our galley that dispenses the hot water. And the water that flows into our galley comes from this machine. It's a series of pumps and filters. And this is all part of the habitability design that you need to put into your spacecraft. You need pumps and filters so that the water you drink and the water that you use for making tea and coffee is nice and clean. Now, where does the water come from that goes into the pumps and filters? It comes from this piece of equipment. That circular structure is part of a zero gravity distillation apparatus. So we have a still on space station that we can make distilled water from, and that distilled water then goes into the previous piece of equipment for more filtration. Now the water that goes into this distillation outfit comes from this mess. And this looks like a plumbing mess. And that's because that is exactly what it is. And if you're thinking astronauts need to be half plumber and half electrician in order to be able to keep all of these systems that are required to keep you alive, you need to keep the systems alive so they in turn can keep you alive, and you have to know how to fix them. And that takes plumbing and electrical skill sets. Where does the fluid that feeds this set of tubes and pumps comes from? Here. And if this looks a lot like a toilet, that's because that's what it is. And that yellow thing that looks like a funnel connected to a hose, well, that is a funnel connected to a hose, and you can imagine what you do with that funnel. What we've seen here are the pieces of equipment that make the habitability in your spacecraft possible. And you start off with the toilet, and you go through a plumbing mess, into a distillation outfit, into a bunch of filters, into the galley, and then to a proper cup of coffee. What we do on orbit, the first thing when you get up is exactly the first thing people do here on Earth. The second thing we want to do on orbit is to make a cup of coffee. So we float around the corner to where the galley is, and you can hear all the machinery. The pumps are pumping, and it's going chugga, chugga, chug and whirring, and you can hear gurgles and things, and you make yourself your proper cup of coffee for getting started on that day. Now, the NASA engineers called this system a regenerative life support system. And I like to call it the coffee machine, because this ensemble of equipment has the uncanny ability to turn yesterday's coffee into today's coffee. And this is part of what it's going to take from a habitability point of view when you are designing spacecraft, particularly future spacecraft for long-term departure from the Earth environment. We're going to have to roll around every drop of water. We're going to have to be able to recycle, reclaim, and reuse. And we are learning how to do that on the International Space Station in this example of our coffee machine. So, with that, let me sign off from my kitchen. I need to get back to teleworking on the lunar lander, and maybe we'll have a coffee machine available on our lunar base. So long.